So, welcome back, or welcome to the course. You won't necessarily be lost if you're just joining us here in the second session. So last week, we took a fast and somewhat oblique introduction to Raman spectroscopy. We didn't talk too much about what people actually do with it. So today we're going to talk about what people do with Raman and how they do it. So just first of note, you're going to see many different flavors of spontaneous Raman scattering. We didn't draw a distinction between spontaneous and stimulated Raman, mostly because stimulated Raman is a lot more complicated, requires a lot more hardware, in my opinion, and is a bit more specialized, or at least niche, perhaps because the experimental techniques are more difficult. That's okay. So when I say Raman here, I just want to clarify that it's spontaneous Raman. You're going to see a lot of different variations on a theme, all different applications and different uses and different geometries. But keep in mind there's more similarities than differences based on the core ideas that we discussed last week. And then of course, I'm not going to talk about it, but except for cars, which is coherent anti-Stokes Raman, it's totally different almost. I mean, it gives a lot of the same information, but it's a pretty wild, ultra-fast technique. Maybe we'll get to that someday, but not for the intro course. So if someone says I do Raman, chances are you'll understand more or less what they're doing, unless they're doing some kind of stimulated Raman type measurement. Then all bets are off. Just ask them what they're doing. I'm sure they're happy to talk about it. Further, I just wanted to point out you're seeing a lot of these, or I'm presenting a lot of this stuff through my own prejudiced viewpoint. So I'm seeing these things through my experience, and I'm biased more towards soft materials, so organics, I guess anything that's not a hard crystalline material maybe. I'm usually looking somewhere in the condensed phase, so there's a whole world of gas phase Raman that is potentially very interesting. And I'm personally biased towards using modular or research type equipment, so not a ready-made Raman microscope system. I would love to talk about those more if we get some time, and they're fantastic tools, but usually we're talking more about the very fancy Lego kits of optics and discrete parts for detectors and spectrometers and optics glued together with optomechanics in a kind of extensible and reconfigurable way. So I just want to say sorry in advance for giving you this little keyhole view, but there's a whole world of stuff out there, and I'm sure that hopefully this will whet your appetite for more of it. It works by the same principles, but oftentimes the purpose-built systems are a little more polished and maybe operate faster and so on. So before we go too much further, I just wanted to put a reminder out there for what Raman spectroscopy is. It's possible that you've missed the first presentation, and no problem. It's been recorded and you should be able to access it through the Andor Learning Center. But just a quick reminder, Raman spectroscopy looks at light that is inelastically scattered off materials. And I added a little cartoon to this slide where I show up here incoming laser light of the frequency omega laser hitting a vibrating diatomic molecule, and you can see my little vibration lines here, and then scattering off both as the elastically scattered, same energy as the original laser, and also inelastically scattered light that is shifted plus or minus the vibrational frequency of the molecule. So that's what I mean again by elastic scattering, same rubber ball, elastic ball bouncing right back up to where you dropped it. And then inelastic, this is dropping the clay ball and it hits the ground, loses a bunch of energy or a bunch of momentum. Its frequency and intensity of peaks show which bonds are present and much more. And we're going to get into the much more part during this presentation. So remember that Raman is a vibrational spectroscopy, and let's think about that in terms of classical harmonic oscillators here for a minute. So balls on springs. So we have my cartoon picture of a diatomic molecule, which is two masses connected by a spring. The masses have mass m, and the spring has springiness or spring constant k. The frequency of vibration of that system, so how fast that is going to go bamba, 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 is proportional to the square root of the spring constant over the mass. And this, of course, like I mentioned, works for other vibrational spectroscopies as well, as far as I know. but we can kind of see if the masses get bigger, the frequency goes down. Larger masses move more sluggishly. If the spring gets looser, frequency goes down. So if the spring is less springy, it bounces back and forth less well, or less fast. And just to connect this back to Raman, it works kind of like you would think. So here's our benzene. Is this animated? There we go. There's our benzene vibrational mode, where the protons are all bouncing back and forth. And this is one of the two strong of Raman modes that you can see for the benzene spectrum. And if you want a refresher, go back to the first presentation. If these are hydrogens, then the Raman shift is 3062 wave numbers. Now, if they're deuteriums, if these are deuteriums instead of hydrogen, which are heavier, quite a bit heavier, then the Raman shift is a lower frequency, as you can imagine. Larger masses on here, and they bounce back and forth slower. So it works kind of like you expect. The Raman shift is actually about 2/3 as energetic there, so you get it at 2293 wave numbers. And you can already think, wow, I can use Raman for isotope identification. And there are situations in which you can. I just wanted to throw in one of these things. You can also look at when bonds get stronger or weaker, if electrons are pushed into a bond or pulled out of a bond. I don't know how much we're gonna touch on this today, but we're gonna see some other interesting applications for Raman shortly. But first we're gonna talk about the prosecution of Raman. How is it actually done, the logistics? A little bit anyway. So what do we actually need to do Raman? That is to say, to actually get the measurement. Well, let's kind of go into this with an idea of our bill of materials or our requirements. So first things first, we need extremely monochromatic light source, almost always a laser. Originally, it was some kind of mercury lamp, pre-laser, but these days it's some kind of laser. A sample, which is to say something that Raman scatters. Optics to get light to the sample. Optics to get light from the sample. Sometimes they're the same optic, like a microscope objective used in epi mode. Optionally, and maybe not optionally, but strongly recommended, some kind of filters to remove the elastically scattered Rayleigh light at the same energy as the laser. A spectrometer to separate light by wavelength, otherwise your spectrum won't be a spectrum, it'll just be an image of your scatterer. And some kind of sensor or camera, or in the old days, photographic film to record the scattering itself, the spectrum itself. So I showed you this terrible cartoon diagram last week, and then I immediately felt bad about it afterwards. It's so vague. So how are you supposed to actually picture a real world system that measures Raman scattering using this block diagram? So I show the laser emitting or sending one monochromatic single wavelength out, or at least a very narrow band, hitting the sample. There's rays. Now there's an extra sideband at a longer energy or a lower energy coming out to the spectrometer. The spectrometer feeds the camera. So if I were to tell you, go construct one of these, you'd say, oh my God, I don't have any idea how to start. So let's talk about some concrete examples here. So let's start with a very straightforward and very, to my mind, cool application, or maybe demonstration of an application, a DIY Raman spectrometer. So this is Raman scattering at home or on the go. So these people, and I hate to use the asterisk there to imply they're not people, I just wanted to put the reference there, made a minimalist Raman spectrometer from a laser pointer, digital camera, diffraction grating, and some filters. Total budget was $3,000. This is a few years ago, so maybe it's a little bit more expensive now, maybe not, depending on how much you spend on the camera. They spent about $1,000 on the Canon EOS, that's like Dawn 70D. So here's let me get my laser pointer. Here's the spectrometer integrated onto the camera. Here's the laser and the sample chamber. We'll go through this in a second. And with this simple system, they were able to get a pretty great looking, I'm gonna upgrade that from good to great, looking benzene Raman spectrum. The x-axis here is in pixels, so ignore that for the moment, but we remember the principal two peaks from last time. And it's not rocket science. Not that I could do this in a weekend, but it's within the realm of human possibility to make a Raman spectrometer pretty simply and to measure spectra with it without it being a huge research project. Although these guys did a fantastic job of documenting everything that you can follow in their footsteps. And that's going to be a theme of this whole presentation, is how good we have it in terms of standing on the shoulders of giants with these projects. So we're able to leverage the work of others. Let's take a quick closer look at this homemade spectrometer before we get into other specific applications. So first, light from a 532 nanometer green laser pointer passes through some cleanup filters. We'll talk about what those are in a minute and why they're useful. Through a sample, the sample's here. The sample scatters some of that light, but also a lot of it passes through unchanged in energy. It goes through an edge filter. That edge filter, which I'll talk about again in a second, hopefully blocks off the residual non-Raman scattered light. That light is then, the light that makes it through that filter is then focused by a lens onto a fiber. The fiber goes to this other box here where the camera is. It emits, the light comes out of the fiber, goes back to free space, bounces off a flat mirror, gets diffracted by a grating, and then gets imaged by the camera lens onto the camera's sensor. So there's no separate optics other than the camera lens for focusing, for collection after the fiber. But we have all of the pieces of our checklist before. We have a light source, we have a sample, we have optics for getting light to and from the sample. We have a spectrometer here. This is a fixed spectrometer that can't be adjusted for angle. It's just diffracting and set up and built in such a way that it sends the appropriate wavelengths onto the camera. And the rest of these, if there's anything else outside of this range that is going to get accepted by the camera lens, we're not going to see it and we can't adjust it. Not to denigrate their work here, it's awesome. This is such a cool project. But it's meant, for us, for looking at a specific band of wavelengths and you can't change the color or you can't look somewhere else. So just to contrast it with the sort of research equipment you might see in a lab. First, a quick note about cleanup filters. And I only want to talk about these because they come into play in so many Raman systems and applications. They're almost omnipresent. So what a cleanup filter is Raman requires a monochromatic source. Why? If your source has a wide spectral bandwidth, so for example, if you're using an LED that has a very broad spectrum, your Raman peaks, because they are shifted relative to the energy that you put in, will also be very broad. And if they're very broad and they're very hard to measure because you're taking a finite amount of energy and spreading it very far in terms of multiple pixels measuring it. Even nominally narrow sources can have some extra stuff in them. So kind of junk light that you don't necessarily want to be there outside of the normal nominal emission. So for example, plasma lines and gas lasers. Also, the 532 nanometer laser pointer that I mentioned before, sometimes those will have the fundamental 1064 nanometer light leaking through. Sometimes a lot of it, which can be concerning. So not necessarily for that reason that we want to do this, but more so just to get rid of anything. Remember, anything outside of our nominal emission. Remember, Raman is a very weak process. If we have other stuff there, it's going to cause a lot of trouble and overpower the signal we're measuring. So what cleanup filters do is they clean up the signal that goes in. So we want just this narrow spike of wavelengths going in there. So in this paper, they use a 532 nanometer center. That's where that emission is going. Where that emission we're going to just let that through, with a 3 nanometer bandpass or 3 nanometer spectral width. So that doesn't mean that the filter itself is 3 nanometers thick. That would be very difficult and easy to punch out if you're not careful handling it. Even if you are careful, a gust of wind would do it. What it means is that we have our center design wavelength, and then it will let through a nanometer and a half on this side, a nanometer and a half on that side, and let kind of this narrow range of wavelengths through. Also, this filter is OD4, optical density 4. That means that outside of our window of transmission, we will tamp down on that whatever light at that outside of our area by a factor of 10,000. OD, optical density, is a logarithmic scale of attenuation. So it means 10 to the 4. So OD1 would be a factor of 10 attenuation, OD2, 100, and so on. So here is the transmission spectra of a very nice looking, moderately expensive cleanup filter centered at 532. This is in my opinion, a miracle of modern engineering. So these are thin film interference filters that are made of stacks of alternating dielectrics, and they can have incredibly precise transmission properties. They're also very sensitive to the angle with which you set them. So if you were to rotate that filter a little bit to the side, that wavelength that it's passing through might let it go, it might wobble a bit side to side. So you generally need to keep them pretty close to normal, to the light coming through. We'll talk about that also a little bit later, but just as another aside to an aside. So just a quick cautionary tale about the hazards of working without a cleanup filter. So this is trying to troubleshoot a problem that we were having where we were getting some mysterious lines in this Raman spectrum. Turns out the helium neon laser we didn't have a cleanup filter in front of it. So even though it's supposed to look like this, a beautiful sharp monochromatic emitter at 632.8 nanometers, if you were to look way in down here in what's in the noise in this full spectrum, you'd see some other lines coming from other transitions of ions in the laser tube. So depending on the laser, a small amount of power can show up there, and it can look just like Raman peaks. So just a warning, use a cleanup filter, and even if you're using a cleanup filter, make sure that look at something inert that's not supposed to scatter in a particular area, and make sure that what you think is coming from your sample is actually coming from your sample. And one more note about filters here, they're also using a long pass filter to filter the light coming out of the sample. And the purpose of that filter, of this filter, is to get rid of any of the remaining un-Raman shifted light coming through the sample. So we want a filter that will pass all of our Raman shifted light, which is just a little bit lower energy, a little bit longer wavelength, and we want to attenuate, just completely stomp down on our original laser light. Keep in mind our original laser light, the amount that's not Raman scattered, is going to be so much stronger, a million or something, a billion times more so than our scattered light. So we need a really good filter that's going to do this. And the closer it is spectrally to the laser, then the lower frequency Raman bands, Raman modes we can see. We can get more and more information at the low range of vibrations. So here is an edge filter, again, a fairly expensive one. Well, I mean, expensive, $1,000. So I wouldn't want to pay that out of pocket, but in terms of research expenses, it's not that much. It is nicely designed, super sharp here on the cutoff. So we want to block our laser, but we want to block our laser very effectively, but we also want to transmit our Raman scattered light very nicely. So I'm going to show, so here's where it's blocking the super sharp edge. Here's where it's flat. Very close to the laser line, close to 532. And here's a less expensive, but still pretty good. I mean, $75, what can you get for that? So you can see it's a little bit less sharp of a line, a little bit less sharp of an edge, a little bit of ringing here, maybe not quite as close. I really had to dig around to find one that looked this, didn't look quite as nice. But even then, for $75, come on, that's amazing. Filters have gotten impressively good, even on the budget end. So I'm so sorry, an aside to an aside, filters of the past. So we talked about the discovery of the Raman effect about 100 years ago. What kind of filter would C.V. Raman have actually used? So he mentions a blue-violet filter and a yellow-green filter, but doesn't say a catalog number or something like that you would see today, probably because there weren't catalogs in the same way. It was almost certainly a colored glass filter, hard to tell which one from his description. You can still buy these today, and the advantage is that they're insensitive. One of the advantages, I mean, they're cheap. One of the advantages is that they're insensitive to angle of incidence, so you can rotate this filter without worrying about exactly how the transmission properties are going to change. So you can see that this is from an older catalog publication of different edges of different colored glass filters. So you can see that you could buy, depending on which one you wanted, any kind of these long pass filters, and this probably would have been something like the filters that Raman would have used. I couldn't find the exact one, but I'd love to research it a bit more. And just as an aside to an aside to an aside, does anyone remember one of these? So these are incandescent black lights from way back in the day. And it uses something called Woods glass, which is a doped glass of a similar type that passes UV but doesn't allow visible through. So when these came out, when I was a kid, it was always party time, with the black lights. And here's a picture that my head is blocking of a yellow-green colored glass shot glass filter, SCHOTT, the glass manufacturer. So I apologize for the nested asides here. Let's get back on. Oh no, this is one level up, an aside, but detector sensitivity. So I'm trying to just draw a starting point for equipment in terms of here's the minimalist setup made out of stuff you could probably find in your house other than sending away for the filters. So I keep claiming Raman scattering is a weak process. It is a small signal and it requires a sensitive detector. So the detector they're using is the detector that comes with the EOS 70D DSLR, which is an uncooled 4-micron pixel color CMOS camera, which is great for taking pictures of your friends or nature or a sunset or something like that. So why is this not an optimized detector for Raman spectroscopy? And again, I'm not judging. I'm just saying this spectrometer is really cool. So uncooled means it's going to have a tremendous amount of dark current. 4-micron pixels, that means we're oversampling probably in terms of using too small pixels to measure our spectrum. It's color, which means it has a filter over the pixels where you're throwing away about 2/3-ish of the incoming light. And it's a CMOS camera, not a CCD. And again, maybe not a big deal, but generally CMOS cameras have higher dark current compared to CCDs. All right, an aside to an aside to an aside. Again, I'm sorry, it's going to become more streamlined as we go through the presentation here. But a better detector, so more sensitive cameras capture more signal with less noise. So the signal to noise goes up with a more sensitive camera. So you can explore signal to noise a little bit with the Andor signal to noise calculator, and I apologize for not putting this as a discrete link. There's the link, andor.oxens.com/signal to noise calculator, or just search. And I wrote an application note about what SNR, signal to noise ratio plots mean in terms of we show these things, what does that actually mean? So if we're comparing one of our CCDs that are purpose-built for spectroscopy, the IDIS DU416A, to this DSLR sensor, and this is my best guess about its parameters based on some forum posts of people who compare different sensors and cameras, you can see that generally the IDIS is quite a bit higher in terms of the signal to noise ratio than the consumer camera, as you might expect, as we might hope. And depending on the number of photons that are arriving per pixel, per exposure, then that might change quite a bit. So the camera, say at this fairly low light level, the EOS camera might have a signal to noise ratio of 1/2. And that doesn't mean that you can't see anything. It just means that it's really hidden in the signal here, or it's hidden in the background. So this is our dark current coming in here through the uncooled sensor, or due to the uncooled sensor. Whereas under the same conditions, we might get something that looks more like this with the IDIS spectroscopy camera. So I mean, that's kind of the difference. That's a really rough illustration of the difference between using a consumer-grade DSLR and a purpose-made spectroscopy camera. So we're taking a roundabout view through some equipment choices here, through how these setups are made, just trying to create some, what's the word, sense of scale for different performance and what you need to record these beautiful spectra that you see in these references that I show, these papers that I show. So, all right, application 1. Detecting food adulterants, a discussion of Raman practice. So this is someone putting Raman spectroscopy into play in the field, or at least getting ready to. So background, food adulterants, not going to go too off the deep end on this one, although I would love to. So what are they? They're foreign substances added to food. Possibly harmful, but at least not what you paid for. So how do you quickly test a complex mixture for specific harmful impurities? So, well, we could try Raman spectroscopy. Why? Fast, non-contact, lends itself to hyperspectral imaging, so you can see spatial variation where you'd measure the spectra in one way or another from here, some matrix or a series of lines, and learn something about, oh, there are clumps of this here and this here, and it can differentiate between two otherwise optically similar substances, which can be very difficult. I'll show you in a second. Here's a picture of, this always comes up, it's the case of Humbug Billy in Victorian England, where a bunch of people were poisoned with arsenic that was replaced with plaster of Paris. Complicated story, because it wasn't just about food adulterants, it was about putting in the wrong food adulterants and trading something that was probably more expensive, arsenic trioxide, for plaster of Paris, which, although gross, is inert. This just always comes up when you search food adulterants. It's just a classic story. Unfortunately, several tens of people died at least, so I'm not trying to make light of this, but it's just something that happened. So here's a Raman spectrometer for food. It's very similar to the last setup, the homemade setup, or at least the educational setup, but now one of the differences here is that we're using, instead of having the excitation and emission share the same pathway, we're using a dichroic filter, and I will maybe take an aside about that, but it's another filter that's used to pass one color and bounce another. So as well, our optics have now become a microscope objective. So here's the actual system here. It's one of our cameras going through a small spectrometer, going through some optics to combine and separate the light, going through a little sample here. So what can you actually do with this? Well, they show that you can detect Congo red and Sudan dyes in paprika. And at first I said, why would you want to do that? And then I said, oh no, are people really substituting red dye for paprika? Red dye is probably a lot cheaper. And now I have to worry every time I eat paprika that I'm getting some kind of food adulterant to make it extra red. So you can see these three powders here. One of them is paprika, one of them is Congo red, and one of them is Sudan. And I can't remember which is why you might want to consider this technique. I think this was the paprika because there's the most of it, but I'm only 40% sure. However, paprika powder is easily separable in the Raman spectra from Congo red and Sudan dyes. So you can see that here, without even knowing anything about the nature of these vibrational modes or whatever, and it's not necessary that you actually know these, but if you have a quiet region here in the substance that you're looking for, and you have these peaks coming in on the adulterants, then you can see pretty quickly that you're going to be able to detect fairly sensitively if you have this or this mixed into this. So this next one is something I couldn't believe actually worked until I saw people do it. And someone originally came to our lab when I was in graduate school and asked if we could measure the Raman spectra inside of some bubbles in the volcanic glass that they had. And I said, no, of course, nobody can do that until I saw people do that. So let me go ahead here. So some minerals have tiny fluid bubbles trapped inside. So think a much more boring but scientifically interesting version of the Jurassic Park mosquito in amber. The composition and pressure of these bubbles are useful geological clues because they're a little time capsule. So how do we probe these mini time capsules? So they're microscopic, must be non-contact because they're sealed under pressure inside a transparent rock, and it requires chemical specificity. If only I knew of a method that was good for this sort of thing. And here's some images of bubbles of various inclusions of various types inside different minerals, and I encourage you to check out the field. I think it's somewhat contentious about how to interpret them, but it's really interesting and it just seems impossible, which is so fascinating to me. So if we have a microscope and a Raman spectrometer, fluid composition can be measured. So here's a Raman spectrum showing peaks from CO2 and no peaks from nitrogen or carbon monoxide. So we can actually look at, well, we, meaning these guys, with great difficulty and effort, can set up an instrument and simply look inside with a microscope and detect not just the constituents, chemically what's inside, but their pressures. And I know you're thinking, and wait, did you say pressure? That's right. So far, we've only talked about identifying chemical bonds. So we can say there's this bond present, maybe vibrating at such and such a frequency. And then maybe we could even say something about the concentration in that if that scattering goes up, there must be more of that molecule there. But what we can look at is that there's a special feature of the CO2 Raman spectrum. It has a spectral dyad here. And this pair of peaks has an odd quantum mechanical interaction. So these are two vibrations that interact with each other in a weird quantum mechanical way that I encourage you to look more into, which is outside the scope of what I can talk about here. But the separation between these bands, the delta that they're pointing out here, goes with density, and they use that as a proxy for pressure. So what you can do is view inside of that microscopic bubble and measure not only what gases are there, but by how far apart those CO2 peaks are, you can actually tell something about the pressure inside. And the pressure inside tells you about the pressure outside when that rock was formed or when that inclusion was formed. And now you're saying, wait, did you say temperature? And I'll say I didn't, but you may have seen the little marks on the previous slide where there's another quirk of the CO2 Raman spectrum. It has another interesting feature, which are hot bands that scale, as you might expect, or as the name might suggest, with temperature. So if you were to plot at constant pressure or constant density, the intensity of these bands relative to these bands, so these two guys relative to these two guys, then you can actually measure the temperature pretty precisely just using spectroscopy, or just using Raman spectroscopy. So not only, this is a spectroscopy where not only can you measure composition, but you can also measure pressure and measure the pressure and temperature independently. These are two different degrees of freedom. One is the split between those two bands. The other is the intensity of the side bands. So there's a lot of cool spectroscopic hooks that you can look into there. And that's one of the things that to me is the most interesting about Raman is that, or maybe I already said that, but it's a thing that's very interesting to me about Raman is that it's this huge mansion with lots of different secret rooms that you can get into and just look at little features that you may not have noticed or that may not be clear from the outset what they mean, but they're telling you something about the very, very closely about interactions within the molecule, about symmetry in the molecule. And this is something that you can't necessarily do if you don't understand what's going on. Not that I always do, for sure. That's an understatement. But you can, again, ride on the coattails of other people's excellent, very insightful work and use this as a tool for doing your own work. So I should have mentioned that that's not the only way of doing Raman thermometry. There are many ways, or at least several more ways, of which I'm going to cover one more. But what if you were to say, well, that's all well and good if you're studying carbon dioxide. Carbon dioxide is not necessarily the thing that everyone is jumping to work with. I mean, it's everywhere at a few, parts per thousand or whatever it is. Unfortunately, seemingly more and more these days, but there are other systems that we're working with. So as we recall, Raman is a vibrational spectroscopy. So you can imagine that when temperature comes in, temperature and vibrations are quite related. Molecular vibrations are temperature. So temperature can be read out in several ways, one more of which I'm going to talk about real quick. If CO2 isn't relevant, what about water? So if you've ever looked at the Raman spectrum of water, well, you're about to. This is the principal feature, Raman feature of water, which is a broad blob of a series of bands at around 3,400 wave numbers. So one of the very interesting things about this feature is that it actually changes shape with temperature. So there's a hydrogen bonded OH stretch and a non-hydrogen bonded OH stretch. And depending on the temperature of the water, those two parts of the peak will go up and down. So what can you do with that? Well, you can measure the temperature of water, and water is everywhere. So here's one particular application where, and this is a group that is looking at a PCR microchannel, so a polymerase chain reaction, you're flowing liquid through here, and you want to maintain a stable temperature of 55 C. So that would be very difficult with a traditional, even very small thermocouple, or many other ways of measuring temperature spectroscopically. But if you can do water, well, the water's already there. Let's measure the Raman spectrum of water. So what they do is they aim their beam around here, their probe, their optical probe, and they look at the temperature here, along that track. And they can actually indirectly measure temperature variation. Next application, SIRS. We haven't talked about what SIRS is yet. I'm going to go through it very briefly and very superficially, but we'll at least recognize the existence of SIRS, why people keep coming back to SIRS. What is SIRS? SIRS is surface enhanced Raman spectroscopy. What does it actually mean? Well, as it says on the label, it's Raman spectroscopy that is enhanced in strength by interaction with a surface. That surface is usually, I think almost always, gold, silver, maybe copper, but some kind of coinage metal. So SIRS, surface enhanced Raman spectroscopy, can be as strong as fluorescence. And everyone says, wow, the specificity of Raman with the intensity of fluorescence, I got to get in on that. But there are some caveats here. There's some rules, some drawbacks. The scattering molecule has to stick onto that roughened metal substrate. It's only going to get enhanced while it's interacting with the substrate. The SIRS substrates can be unpredictable in terms of performance, lifetime, reproducibility, and the surface can interact photochemically with the things that are sticking onto it. So you can have that surface doing photochemistry or whatever catalysis with your analytes. So the thing is, people keep coming back to it because it has such incredible promise, but there are many experimental challenges. So just to give you a taste of why people get hooked on SIRS is that this is, the authors claim, a SIRS spectrum of single adenine molecule. So single molecule Raman scattering, yes, that's right. People are doing this sort of thing. And as you can imagine, it sounds so crazy. It is a very contentious field. I don't know as much as I could about it. I am not a SIRS expert. Ooh, but I'm taking it aside first. SIRS substrates. Uh, so the original SIRS substrates were just colloidal metals, sort of a metallic pond scum. So if you have metal ions in solution and you reduce them, reduction is gaining, yes, oil rig, then you form sort of metallic pond scum on a microscopic scale. Maybe nanoparticles, maybe microparticles, maybe clusters of nanoparticles. So there are now more regular commercial substrates that you can still, it seems, buy online. And in either case, whether it be colloidal metal or metal grown on a surface or whatever, the goal is metallic nooks and crannies, which act possibly like a satellite dish to focus the electric field of light or something. But you can see here, here are some TEM images, I think, of some colloidal metal particles from 20 years ago. And then here's a commercial, an SEM of a commercial SIRS substrate. But you can see in either case, you want something that looks like some popcorn or clusters of metallic particles. And you want your analyte, whatever you're looking for, to get adsorbed on there and start to light up in terms of SIRS. So what could you do if you could measure Raman scattering from a tiny, tiny volume of space, maybe even potentially from single molecules? So these folks are watching a macrophage eat a SIRS active gold particle. So they've made a gold particle that on its surface can adsorb or can interact with molecules in its environment and then light them up and make them SIRS active and make them scatter like crazy with their Raman spectrum. So what they do, and this is incredibly cool, is in my opinion, is they let a cell eat that particle, endocytose it, or bring it into its internal environment. And then as the particle moves around the cell, so imagine, you eat this, you're in your environment, you eat this glowing orb, this gold nanoparticle, and it goes into your mouth and it travels through your digestive tract. That's what it's doing with the cell. The cell, of course, isn't a guy or an animal. It's, has vacuoles and stuff or whatever they are. But it brings it into its environment and it traffics it through and it interacts with it. And as that nanoparticle bounces through and goes through the cell, it starts to light up with different spectra because it's showing you the chemical environment of the part that it's accessing. So you can see that here's a little photomicrograph, dark field scattering of, and they're showing this tiny particle which you can barely see. And then this is a time trajectory as they track it around and measure spectra from it. And you can see that over time you're getting not just one spectrum that goes up and down in intensity, but you're getting a series of different spectra that tell about the chemical environment that you're interacting with. And I encourage you to check the paper out because I'm not doing justice to what a cool experiment this is. So again, SIRS is an incredibly powerful way to boost the Raman signal. Unfortunately, or maybe just not unfortunately, but maybe it's got some drawbacks that can be challenging. It's not as simple as throwing a sample into a Raman spectrometer and pressing measure, not to minimize what that actually is. All right, and then last note for today, I might add some more material to subsequent versions, but what kind of camera could you use for this? Because I showed you another camera before, but the camera they actually used for this experiment was an EMCCD. It doesn't have to be our EMCCD, but this is one of ours. And a single or few photon event, so keep in mind, you can see these are, ooh, I can't go back. Keep in mind, you can see that in the previous spectrum, those spectrum were very noisy. There's very, very little light coming through there. So to effectively capture every photon, we have an EMCCD, which combines speed and sensitivity. So not only are we measuring spectra that are super weak, we're also trying to measure them on a very, very fast time scale. So what these cameras do, and this is different than a conventional CCD, is that there is an additional set of registers here. So you absorb light here in the imaging section, gets converted to electrons, or it excites electrons that can stuck in these pixels, gets shifted down, and then gets sent down these readout registers to a multiplication register. So there you have on-chip electron multiplication, which is kind of like a PMT or an APD, and it gives you sub-electron read noise. So that is to say that you have extremely, extremely low read noise, a very, very low noise floor, and you can measure spectra that are just, handfuls of photons per peak or something like that. Very, very, very weak signals. So just an aside on detectors in terms of what works for one thing, we went all the way from a commercially available camera that you might get at Best Buy, well, not commercially available, consumer grade camera you might get at Best Buy or off Amazon, and now we're at these very specifically designed ultra high sensitivity cameras, and we kind of saw that range of sensors real quick. We should definitely talk more about sensors, but I'm already at almost 40 minutes, so I wanted to leave some time for questions. So it's been a bit of a whirlwind today, and unfortunately that's all I can fit in. I wanted to put about 3 more things in, but I didn't want to make it a full hour because that's a lot to listen to me for. So join us again in 2 weeks for my colleague Shane Harrell's discussion of 2D semiconductor characterization with Raman. Sorry, I keep slipping back and forth between those 2 pronunciations, and I think the second one is correct. And I apologize if I didn't get to your favorite method. So on the other hand, is this too simple for you? Is this too high level or low level? Is it too low complexity, too high of an overview? There are some additional guest speakers who are contributing much more in-depth, cutting-edge work that is incomprehensible if you're not already part of that community sometimes. But I encourage you, if you're interested in seeing what people are doing on the front lines with Raman, to check out the Andor Learning Center, where we're going to post those coming soon. I'll have a schedule for that very soon. And otherwise, please if any questions have come up, let's talk about them now. Again, thank you for your attention. It's been just about 40 minutes, which I feel is just enough not to overtax our time slot here, and leave a little time for questions. Thank you again so much for your continued participation and attention, and we'll talk again soon after the questions. All right. Oop, hey everyone, am I coming through okay here? Rebecca, can you hear me? Just adjusting. I don't think I need to share my desktop, right? I'm just going to answer some of these questions that have come in.
Yeah, we can hear you, Adam.
Okay, great. Yeah, sometimes it's with no audio from the audience. It's always mine's just speaking into the void. So just a few questions, but good questions. Again, we will share the video and slides as soon as possible. And just to answer these in the order they were received. So we have a question about, for measuring dilutions, we usually deposit a drop on a glass substrate and let it dry before Raman measure. Then we focus on the area of the dry drop. The Raman measure is not good, although we calibrate before the measure. Please, what is a better way to measure Raman dilutions with low concentrations? That's a good question. What I'm envisioning is you're doing this on a microscope with an epi illumination and collection setup, I think. If I'm not getting this right, just chime back in the chat. I think you can do that interactively. I think if you're letting it dry on purpose just to boost the concentration to give you more signal, there's nothing wrong with that as long as you're tracking how much volume you end up with. What I'd be concerned about if you're doing that is that you get a coffee ring effect where you might have a concentration that didn't of the end film or whatever you're ending up with that didn't reflect accurately what the original parent solution was. So if it were me, and what I used to do for small volumes of liquid was to take a cover slip, put a Teflon washer on the cover slip, pipe the liquid into that washer, put another cover slip on top, and basically make a little Oreo cookie where the cookie was the glass cover slides, the filling was a little Teflon washer, and then the volume in between was where I could keep the liquid. That way it stays in a small volume, doesn't go anywhere, and is pretty easy to measure. If the concentration is just too low and you can't see it in the first place, that's a different story. You may just need to evaporate it in a controlled way and get the concentration up without getting precipitates or whatever, without having it precipitate. Hope that addresses that question. So another question about what kind of 532 nanometer laser. The authors actually point out that it is a laser pointer that they bought and slapped some kind of power supply to. So it is a CW laser, frequency double neodymium YAG or ND YAG, whatever you want to call it. So I think you can just buy it. You could buy one off Amazon. Again, if you're going to buy a cheap 532 nanometer laser, keep in mind you may want to invest in some laser goggles to block any remaining 1064 light. I saw a pretty alarming article about how much infrared light was coming out of these green laser pointers because they cheap out on the long pass filters. They're not putting in the right filter to block what's left of the fundamental. So again, continuous wave green laser pointer, and if you're going to DIY that, make sure that you're not going to blind yourself with a surprisingly powerful infrared laser diode. Another question, how to measure Raman spectra of colloidal quantum dots suspended in solvent. All I get is Raman spectrum of solvent. Yeah, you're right. So I didn't cover this discreetly, but the Raman scattering is proportional to the concentration of the scatterers in the volume that you're lighting up. So unless you have a quantum dot paste that's like 90% quantum dots by volume, what you're going to mostly have in a dilute solution is solvent. And if you're doing non-resonant Raman, you will see everything equally. So I don't know a lot about resonant Raman of quantum dots. I assume that you can do that, but other than subtracting out the solvent peaks, then I would look into the literature for pre-resonant or resonant Raman scattering for quantum dots. Simply because you're right. I mean, unless there's some specific target for them, you're just going to see a lot of solvent, and then within those, 1 in a million of that volume is taken up by the actual quantum dots themselves, and you'll get that proportional weak signal from the scattering. So I hope I'm not going too fast here. Does SIRS only apply to individual organic molecules, or could be applied to inorganic thin films? So the danger in answering these questions off the top of my head is that SIRS has been an ongoing and extremely contentious field since before I was born, I think. So has someone done it or tried it? Almost certainly. Keep in mind that most of these things are flowing a solution over or mixing a solution you're looking at with something in it with nanoparticles. There are these amazing things being done with measuring single chains of DNA by sending them through a purpose-built aperture. These I think they're called nanoslits. So I bet you someone has done something like put SIRS active nanoparticles on a PDMS stamp and then stamped it down onto a biofilm. I bet you there's 100 papers on that. So I'm sure someone has, and or you could even imagine flowing dropping a solution on that has quantum dots, that has SIRS active nanoparticles onto a biofilm, then they fall into the biofilm and dissociate with it. So as long as there's some physical contact that has to be quite intimate, I'm sure someone's taking a crack at it. And I'd love to know if you find anything in the literature about that, because biofilms are incredibly interesting, and as complicated as you think they might be, they're more complicated. Let's see. I think I have time for 1 or 2 more questions here. Still working on a good place to start that's free for a catalog of Raman spectra. NIST is a good place that has a pretty significant catalog of Raman spectra that's a go-to for me. So if you just search NIST Raman spectrum or NIST Raman spectrum benzene, that'll give you an example there. As far as something I keep, it's in my homework to have a good free resources for band identification, and I haven't quite figured it out yet. So I'm sorry for not having that prepared yet. How to avoid condensation in a hot stage Raman? I don't actually know. I would have to look into that. I mean, water condensation? It sounds tough. I would imagine flowing dry gas over or something, but I apologize. I don't know enough about that to say anything helpful. Let's see. And I apologize. And again, I'm still behind on answering questions. We got so many last week. If I haven't gotten back to you yet, I apologize. But I thought there was only going to be like 2 or 3 questions here through the thing, and now we've got a bunch, which is fantastic. Thank you guys. These questions are all really actually very perceptive, and it seems that you are in the thick of it working on these things. What else did I miss here? Let's see. Can you please share some examples of SIRS for studying plasmon polaritons and nanostructures? I can't. I checked out of actively being involved in SIRS a long time ago, and I was never that knowledgeable about it to where I could give you an overview of SIRS with plasmon polaritons, because I tried to understand the mechanism, and I did not, and it's not clear if anybody does, or at least no one can agree on it. And that's my ignorant opinion. I apologize if I've offended anybody with that. But it is, I still believe, a contentious field. Is it possible to use low laser power? In general, sure, as long as your detection is good. And again, just want to give you a note about my prejudices. I'm talking about to get these very smooth spectra with super high signal to noise, the kind of things you need, the hoops you need to jump through to get to that. So it is possible to use low laser power, but you have to be detecting very carefully, and maybe you're using some kind of statistical choice as you go through it, rather than getting an aesthetically beautiful spectrum. Any recognizable difference between the Raman spectrum in different phases? Oh, yes, quite so. So what a good question, because I've only showed condensed phase. Raman of gases and vapors is much more, in my opinion, pure, because you have these very weakly interacting molecules that are free to rotate and move around and do their thing. So yeah, you get these very ornate spectra, and I encourage you to look into gas and vapor phase Raman. They're tremendously different when molecules can't see each other and aren't affecting each other. So yes, vapor or gaseous benzene would be very different than liquid benzene, and I can't do it off the top of my head about what those differences actually are, but you would see things like rotational structure and what have you. How does Raman thermometry deal with heat from the laser light used to irradiate the sample? That's a good question. If your sample is picking up, is getting vibrationally excited by the laser, then it is going to affect it. I think it's probably that it's a small enough perturbation that it doesn't heat it too much. You may be heating it with other mechanisms through the laser, but I suppose what you'd have to do is turn the laser and not fry it for a long time. And I mean, that's something that people don't really talk about, is how quickly is your sample going to be destroyed by the measurement method you're using. I know in my past, it's something that you can quite easily do with soft materials and organic materials, where you're blasting this thing with a focused, strong laser beam, and you can, in some cases, ablate or melt or oxidize your sample, photo bleach it very quickly. It happens with biologicals, it happens with soft materials of many types. So as far as dealing with it, I don't know. I think the measurements are short and small enough that they're a pretty small perturbation. Do other materials show hot bands similar to CO2, or are those peaks specific to CO2? I don't believe metals, and you're asking about metals as well. As far as I know, metals don't Raman scatter at all. Pure metals, so please don't at me if I'm totally wrong there, but generally not seen. Other materials do not show, in my understanding, hot bands in the same way. I think those are unique to CO2, at least that exact implementation. And sorry, let me hedge really cowardly here and say that particular analysis is unique in that case to CO2. But I would encourage you to look for Raman thermometry and research it, or not research it, but look into it a bit more. But you to my knowledge, you can't just apply that to everything, for sure. Could you do that to other molecules with a similar structure? Probably, I think. I need to look into that. That's actually a great question. But like I mentioned, that's not even the most popular way of doing Raman thermometry. It's just a neat way. There's another question that someone asked about looking directly at Stokes versus anti-Stokes. And that's probably the simplest way, where you look at the ratio of the Stokes side, where it's the lower energy, and then the anti-Stokes side. And that ratio should give you information about the temperature. The reason that I didn't talk about that is because it leads you down a rabbit hole of low frequency Raman sometimes, because the chances of seeing anti-Stokes emission with spontaneous Raman is really low, and you're not going to get much there at higher frequencies. So it's harder to measure anti-Stokes in the normal geometries, or not normal, sorry, that's normative, judgmental. In the usual geometries that you'll often see, these setups have a hard time measuring anti-Stokes Raman. So the answer to your question is yeah, there are better ways to look at, simpler ways probably to look at Raman thermometry. And I didn't include them because I thought it was a really cool trick. It was a really cool trick, an example of a cool surge trick. Sorry, cool Raman trick. Maybe one or two more questions here. Let's see. Oh, sorry. I hope I answered your question, Evangelos. How exactly do you measure the temperature comparing Stokes to anti-Stokes and the CO2 or the so you could probably measure it with the anti-Stokes ratio, the Stokes anti-Stokes ratio as well. But in that paper they were using the hot bands. So sorry, yeah, little guy, a very technical term, small side bands next to the Fermi diode there. And yeah, you're right. So another question about SIRS, is copper a good metal? I wouldn't try to tell you that it weren't. I don't see it used directly, probably because of what you say, that it oxidizes really fast, so it'd be unstable. I don't see people using copper just in my cursory inspection of the literature once in a while. Typically it's gold, I think, these days, for the reason that it's chemically inert. So yeah, you got me there. But I always see people name drop the coinage metals, which for whatever reason the list often doesn't include platinum, maybe because it would be pointlessly expensive to work with, or palladium too. Is it possible to have both? Last question for now, because it's just about the hour. Is it possible to have both Raman and photoluminescence functionalities in the same setup with having equally good sensitivities? The detector used is IDIS 420, and the materials are usually TMDCs, colloidal quantum dots, and colloidal quantum wells. Yes, you can use, you can use the same equipment for Raman spectroscopy and photoluminescence, as long as you have a light source that is suitable for Raman, a nice sharp laser that's cleaned up a bit. If you're doing that with an LED, chances are it won't work, at least not very well, if at all. And the difference would be maybe you would have a grating that has a higher groove density for Raman, which would give you better spectral resolution, or you have a grating that's blazed in the Raman, around the Raman wavelength that you're going to do if it's somewhere in the near IR. So yes, and I kept saying that over and over again, saying, well, it uses the same equipment as photoluminescence, sort of implying that people would just know off the top of their head what a photoluminescence measurement setup would look like for doing, epifluorescence or something, which is a huge assumption on my part that I felt pretty goofy about later. So the answer to your question is absolutely. That could have quite a bit, quite excellent sensitivity for both. I don't know about equally good, because that's a tough one, right? And the Raman measurements would require a bit more experimental hygiene in terms of how you handled them, simply because it's such a weak process. All right, I think that's all I've got for the moment, because my voice is going to go. And I apologize if I did not answer your question. I will try to, if I can, or at least let you know that I did see it. All right, I think that's all I got for today. Rebecca, is that all right?